All right. Okay, thank you for coming to our last session of the semester. Today we have Ekin here to talk about online Makespan scheduling under scenarios. Before we begin, let us go over a community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, take it away.
Thank you. So today I would like to talk about some recent research of mine. Um, I was a bit unsure about whether or not I should present this here because it's mostly combinatorial optimization and not as much combinatorics. However, combinatorics does make really, in my opinion, good-looking appearances throughout. So I thought maybe it might be interesting to you as well, which is why this will be not a very assumptive talk. I will not assume that you know anything about my research problem. So let's first look at online Makespan scheduling. This is actually like basically the second problem that you learn when you study online algorithms and online optimization. It's basically you are given a set of jobs that each have some processing times, and these are revealed like one job at a time. So every time a job is revealed, you are informed of their processing time. And the task, sorry, there are also a number of identical parallel machines known in advance, which means these are just machines that are supposed to process the jobs, and they take exactly the same amount of time, which is the processing time given per job. So now your task is to partition the jobs into machines such that the make span is minimized, and the make span is given by the maximum time any machine would need to process the jobs. This is just formulated in the realm of machines and jobs and scheduling because it comes from such a background, but in reality, it is just as easy as just having some numbers, which are the processing times, and wanting to assign them to some sets in a partitioning way, such that the largest set has as smallest sum as possible. And the important part of this problem, which makes it online, is that as soon as you are revealed a job, you have to decide which machine you want to assign it to. So you can't look into the future. You don't have any information about what jobs are to come next or what processing times they will have. You don't even know whether there will be other jobs at all. Let's have some example. Let's say we have three machines, which, as you can see, we know in advance. And every time we are given a job, we could assign it to some machine. Let's say the green job we choose to assign to the first one without loss of generality because the machines are symmetric. The second one, maybe we want to put to a machine that is not processing anything right now. Maybe the third one as well. Then we kind of load the first one more because it wasn't as loaded. So now it looks pretty balanced. And intuitively, you want to keep them balanced because the biggest one should be as small as possible. And then another one, and then maybe another one that you have to place somewhere and it looks unbalanced. So as in this particular example, a very common way to draw pictures of such schedules is that you would have the jobs as some stripes and their width kind of represent their processing time. So in this case, the red job would have the biggest processing time. And had you known these six jobs in advance, you wouldn't have scheduled them like this because now the make span given by the sum of the widths in the second machine is way too big, unnecessarily big. You would have put the purple and red jobs together, for example, the green and blue jobs together and the orange and pink jobs together. And then it would have been more balanced. And to estimate how successful you are in online assigning these jobs, you would use the notion of competitive ratio. Competitive ratio is essentially the ratio between how well your optimal value is by what you do, by whatever algorithm you're applying, divided by what would have been the best way had you known the entire instance in advance. So in this case, that would be the width of the red and blue jobs that you see on the picture divided by perhaps the red and purple jobs that you don't see in the picture, but if you rearrange them, that would be the optimum. And if that optimum is always bounded by some factor rho for whatever instance, then we call the algorithm that achieves this rho competitive. Here you see the offline optimum. In fact, I wasn't entirely correct. So apparently the optimal way to do it is to kind of leave the red one alone. That's even slightly better. So this one we call the offline optimum as opposed to the online attained value. And an easy observation to make is that this competitive ratio for this particular problem is always bounded by the number of machines. How come? Well, no online algorithm can output something worse than the sum of the job processing times, because that is like the biggest width you can ever achieve. That's all you have. On the other hand, you can never achieve something that is better than the average load, which is given by that sum that I just mentioned divided by the number of machines, because some machine has to be at least the average or above. So that's like a lower bound on your denominator. And then the ratio between the two is always at most m, which is the number of machines. All right, so far so good. If there are any questions, I'm happy to take them anytime, because that's perhaps a new problem to you. Okay, if there are no questions, then we look at the novel extension of this problem that was part of my research. So now you see the initial problem that we had, again, the jobs processing times machines, and you want to partition so that the biggest load is as small as possible. And now we extend this problem by scenarios. A scenario we understand as a subset of our instance, and we are going to look at multiple subsets of our instance, and we will want to optimize the worst of these subsets. So in addition to what we have, now we are given a number k of these subsets that we call scenarios. We know this k in advance as well. And each scenario is defined as a subset of the jobs. And how are we informed about what subsets we have? Well, every time we reveal a job, we will also reveal what scenarios this job appears in. And then we will want to assign accordingly. So what is our goal now? Our goal now is to optimize the worst subset. So we will want to find the worst machine. That's the inner max you see in the formula. In the worst subset, with respect to the worst subset of jobs, that's given the outer maximum in the formula. So in the formula, the pink parts are how we extend the problem, and the black part is exactly the underlying problem. All right, so now we would like to argue that if we have 3 scenarios and 2 machines already in such a small case, a very simple family of instances reveals that we can't achieve a lot. So we will reveal the jobs just like in the first slide, one by one. And every time we reveal a job, we will also reveal it in the scenarios that it appears in, that you see in the small green boxes. And we will also reveal the scenarios downstairs as S1, S2, S3. As you see, we already know there are 3 scenarios. As of now, there are no jobs revealed, so they are all empty now. But as the jobs are revealed, we will be extending them. So first, we are revealed a green job of processing time 1. The 1 on the job denotes the scenario it belongs to. Since the 2 machines are symmetric, we can put it to the first machine without loss of generality. And then we get a second one. Now there are 2 cases. Let's say we assign it to the second one. Then what happens? The following could happen. we don't know anything about the future jobs while making this decision, so we are not bracing ourselves for the following. Let's say we get another job that appears in both of these scenarios, 1 and 2. Now we realize that we have made a mistake because either we put this pink job to the first machine, and then scenario 1 has a Makespan of 2, or we put it to the second machine, and then scenario 2 has a Makespan of 2. But we cannot change our earlier decisions, right? We have to assign immediately, and that's end all be all. So we can't avoid one of these two situations. Had we known these 3 jobs in advance, what have we done? We would have placed the green and blue jobs together, and the pink job would be on its own. And then we would have had a Makespan of 1, because in both of the cases, the first machine would have 1 job, either the green or the blue one, and the second machine would have had the pink job, again 1, which is of processing time 1. So if we do it like this, then we cannot get anything better than 2 competitive, and this is the worst bound we can get, given that there are 2 machines, and we had mentioned you can't get any bound better than you can't get a bound worse than 2. So this is literally the worst thing we can do. Let's not do it. If we do it like this, then the following could happen. Let's say we get a red job that appears in the first and third scenarios. The third scenario was empty so far. Now it has also received a job. And now, again, for the same reason, we can't assign this to the first one, because then scenario 1 would be unbalanced. And if the instance stops here, then we have lost. So the only possibility is to assign it to the second machine. But now what could happen is the following. Now we could get a purple job that appears in scenarios 2 and 3. And in the first case, what we had with the first 2 scenarios, now we have with the last 2 scenarios, 2 and 3. You may notice that in scenario 2, machine 1 is loaded, and in scenario 3, machine 2 is loaded. So wherever you put the purple job, you are bound to unbalance one of the scenarios. And in fact, had you known that this is the instance, these 4 jobs in advance, then you would have placed the green and purple jobs together and the red and blue jobs together. And that would have given you, again, a Makespan of 1, which is why this way you also don't get anything better than 2 competitive. And there were only 2 cases that we have exhausted. So we conclude that already for 3 scenarios and 2 machines, you cannot get anything better than the trivial bound. So any algorithm is the worst algorithm. So this kind of sounds depressing, and it almost sounds like our little model doesn't have anything else to offer, right? So that's not really the truth. So what we have shown through this little family of instances is only a very small portion of the complexity, like the competitiveness landscape. Because if you have more than 2 machines, then 2 is not the worst bound you can get. You could get, like, if you had 4 machines, then your trivial bound would have been 4. If you had 7 machines, it would have been 7. So if you had like 29 machines and something too competitive, that wouldn't have been bad news. So it's still worth kind of investigating around, like, what happens if we increase the number of machines. Another thing is we needed 3 scenarios to model this little play. However, we could also ask ourselves, could have also initiated something like this had we only had 2 scenarios? That's also a valid question. So these are the main things that we could look at. For the first one, for the latter one, actually, if you have 2 machines and 2 scenarios instead of at least 3, then the answer is it's not as bleak, because you could achieve a 5/3 competitive algorithm. We do not know for the time being whether 5/3 is the best ratio you can achieve with that, but through a similar family of instances that is a little bit more intricate as far as processing times are concerned, we have been able to show that it won't get anything better than 1.650, and it goes on. It's 9 plus square root of 17 divided by 8. So this is a nearly tight bound. It's almost the best possible algorithm. On the other hand, one more thing you could ask. So if I have 3 scenarios and multiple machines, then I could get something better, that I could get something non-trivial, right? So it's easy to observe that you will never beat the bound of 2, but 2 is not the trivial bound for more than 2 machines. Another question is, to obtain this, should I also use like different processing times, or can I again find a simple example that only uses like these square-shaped jobs? Throughout the small example, you might have noticed we only had processing time 1, which is why we were basically able to count the jobs and not take the sum of their processing times. And as it turns out, if you want to get something worse than 2 for more than 2 machines, then you would have to use, if that's even possible, you would have to use non-uniform processing times, because another result is that, and that was kind of a funny algorithm that we modeled as a bingo card. We have a 2 competitive algorithm that works on at least 3 machines if you have like unit processing times. So you will have to create something more intricate. As you can see, it's a very like multifaceted problem. And you also see that in the first column, you have like at first column 4 plus, you have at most 3, you have at most 4, and 4 plus, like the rightmost lowermost entry, you see that it is at most k plus 1. So in some sense, just like you can trivially bound the ratio by the number of machines, you can also bound it by the number of scenarios plus 1, and that's not even tight. Like it will be something strictly better than that. And that follows from like an algorithm that is essentially like a generalization of how you would do it had you had only one scenario, which is like the most classical online algorithm for the underlying problem, where you don't have scenarios, just like jobs and machines. Namely, in that case, a very good strategy is to always pick the least loaded machine. Then you don't have to think about what is to come. You just think of what you already have and what is already least loaded. That gives you a bound of 2 minus 1 over m. For m equals 2, that's 2/3. For m equals 3, that's 3/2. For m equals 3, that's 5/3. Those two are the best possible values. For 4 machines upwards, you have better algorithms, but yeah. So instead of always putting the job to the least loaded machine, what we could do is, I will kind of be a bit fast about this because that's not what I want to focus on today. Instead of saying I want to find the least loaded machine, I want to find a machine that is not among the most loaded machines with respect to any of the scenarios, because the jobs aren't always in the same scenario. So the scenarios might have different loads, or like different orders of loads for machines. As we have seen in the example, it could be that in the first scenario, one machine is more loaded, but in the second scenario, the other machine is more loaded. Then you don't have a well-defined least loaded machine, which is why you want to find a machine that is not most loaded with respect to any of the scenarios. And if you want to find something like that, then you will need basically enough machines. If there are not enough machines, then you can't find something. But if, for example, the number of machines is strictly larger than the number of scenarios, then you could find something via pigeonhole. So you just find this number m divided by k rounded up minus 1. By the pigeonhole principle, there is a machine that is not among top that many, and you find that machine and assign the job to that every time you get something. And that gives you some bound that looks like this if you do the math. And that number is strictly less than k plus 1. And if you set k equals 1, then that would mean there exists, so place the job among the, that is not among the m minus 1 most loaded machines, which would be the least loaded one. So this is indeed an extension of the classical list scheduling algorithm, which is simply always picking the least loaded machine to assign a job. Okay, so now I would like to move on to the actual topic I wanted to present to you today, because as you have seen, the problem is already interesting and non-trivial if you have unit processing times. And if you have unit processing times, the problem has a beautiful interpretation in terms of hypergraphs. So what did we have? We had jobs, we had machines, we were assigning jobs to the machines, and we had scenarios, and scenarios were subsets of jobs. So now let's rename things. Now we call our jobs vertices, and we are revealed one vertex at a time. We are given colors that we know in advance. These are the machines. So instead of assigning jobs to the machines, now we are assigning vertices to the colors, and this already looks like vertex coloring. And now we call our job subsets, the scenarios, hyperedges, which, if you're not familiar with hypergraphs, are basically like edges, but they're allowed to have size more than 2. And we know their numbers, and they're also revealed as the edges, as the vertices are revealed, as like the hyperedge restricted to the vertices as that we already know. And now the goal is to find a coloring that minimizes the highest occurrence number of a color in any hyperedge. So this, this T inverse I intersection SK, that is simply the number of jobs in a machine in a scenario. That's exactly the same formula. There we had the sum of the processing times, but now since the processing times are assumed to be uniform, we just say it's the number of such jobs that are assigned to the same machine. Now it's called color, and belong to the same scenario. Now it's called a hyperedge. And so if we go back for a second, the striking result is that if you have enough scenarios, i.e. if you have enough hyperedges, for any number of colors you have, you will eventually find a hypergraph that you cannot color with competitive ratio better than m, which is still the trivial first competitive ratio you can achieve, because it is still the same problem, in fact only a special case of it. So today I will show you how we can prove this for m equals 3, and I will then talk about a little bit about the consequences for other m. For m equals 3, the nice number I have found is 233, which looks like a typo, but it isn't. If you have at least 233 scenarios, then you can find a family of instances such that no algorithm can solve this auxiliary hypergraph coloring problem with competitive ratio better than 3. And again, you have 3 colors, so this is the worst you can do. And for that, our goal is to find a family of hypergraphs that is really as simple as possible. So what I show you in the following is more of a wish list than like some actual claim. I will like each hypergraph to have hyperedges of size at most 3. And what I want to do is, I want the offline optimum to be 1. So I want the hypergraph to be offline colorable, i.e., if you know the entire hypergraph in advance, you can color it in a way such that in every hyperedge, there are 3 different colors. So each hyperedge has at most 3 vertices, and they're all different colored. However, on the other hand, I want any online algorithm to force a monochromatic edge on one of the hypergraphs of size 3. So in the end, what will happen? Any algorithm will have a Makespan value of at most of exactly 3. But had we known the entire instance up top, we would have been able to have colored it in a way that gives like Makespan 1, because in every hyperedge, i.e. in every scenario, there is exactly 1 of each color. So if in case it's not clear right now, I hope in the next slides there will be more pictures. What we do is the following. So we thought of this nice gadget that we have that consists of 7 vertices and some hyperedges. And we ask ourselves, so we basically release copies of this gadget and the algorithm colors it in a way. And we will kind of release it and connect it to other copies such that it is 3 colorable. So as of now, it is, but we will also connect multiple copies of it with each other, so it won't be clear in the end, but we will have to be careful about this. So let's say the algorithm colors all 7 of these vertices, say blue. What happens then? Then we have already won, because then the algorithm already has a monochromatic edge, for example, 1, 2, 3. But this graph is 3 colorable, so the competitive ratio is already 3. So we may assume that this doesn't happen. The algorithm colors this gadget if we release a copy, either with 2 colors or with all 3 colors. So if it's colored in 2 colors, then you will have to believe me that the gadget is created in such a way that if we release 7 gadgets, then we have a sub-hypergraph like this. And if we have achieved this situation, and now the colors like red, blue, and yellow, this comes from like a feasible coloring that I'm not showing to you so that you can still understand what's going on visually. If we can color this subgraph in that way, such that the algorithm has partitioned among J1 and J2, so the rows that you see correspond to the colors that the algorithm has picked, and the actual colors that you see is our offline coloring, which should have Makespan 1. If this happens, then we play some sort of an end game, namely we release a vertex that is connected to the leftmost 2 copies in the way, and we color it yellow. Now the algorithm is forced to place this vertex to the 3rd color, because if x1, the yellow vertex that I just added, this one here, if it were placed to J1 or J2, then that would be a monochromatic edge as far as the algorithm is concerned. So that wouldn't be allowed. The algorithm is forced, therefore, to put it to the set J3. And now, so that's 1. So far, the algorithm has survived it. We have survived it. Next, I reveal something like this that I also connect to x1, the most recent vertex, as well as the middle 2 subhypergraphs. And once again, the algorithm is forced to place it to the 3rd online color J3, but we can still color it red. And now you may notice something. In all of the 3 colors, J1, J2, and J3, that the algorithm is picking, there is a monochromatic edge of size 2, right? So the algorithm, like look at the 6 vertices, J1, 5, J1, 6, J2, 5, J2, 6 on the right, and x1 and x2. The algorithm was forced into using all of the 3 colors to color these vertices. On the other hand, we were able to color them only in 2 colors. So now we can exploit this and reveal one last vertex that we color blue, which is our not taken color in this case, and we connect it to the 3 pairs that were already there. Now the algorithm has to create a monochromatic edge, no matter which online color it picks. In the picture, I put it to J3, for instance, then you see that X1, X2, and Vn create hyperedge where all of the three vertices are assigned the same color, J3, by the algorithm. However, the actual coloring that you see in the picture, that is our offline coloring, and there we have indeed a Makespan of 1. By Makespan, I mean like the colors are pairwise different in a hyperedge. And you will have to believe me that the parts that I haven't shown you in this picture, so that the picture is somewhat understandable, those are also in the same situation. So that's the first case. And so basically, if the algorithm receives 7 gadgets that assigns to 2 online colors, then it's bound to lose, because then we have this end game that we can play. So therefore, we assume that if we release many copies of the gadget that we started with, this one here, at most 6 times, the algorithm will want to color it in 2 online colors, because the 7th time it happens, we will be able to play this end game. Therefore, we will have to look at the other case where the algorithm uses all 3 colors to color this gadget that we release. This is a bit more complicated, but we still want to obtain the same situation. So this is what we had at the end, right? We had like some hypergraph. The algorithm was forced to create like a an edge in this case of size 2 in each color. And this entire graph, we were able to color such that these 3 edges in 1 online color each, for them we use 2 colors. In this picture, you see it's blue and yellow. So if I then create another vertex that I connect to these 3 pairs, then I don't have a problem, because I still have a 3rd color to color them, because I only used 2 colors to color those 6. But the algorithm does have a problem, because the algorithm had to use all of the 3 online colors. So whatever online color it picks for this last vertex, it will have to create a monochromatic hyperedge of size 3. So again, this is wishful thinking. That's what we want to achieve at the end. And if the green edges that you see in the picture, if they're not in the same connected component, then as the offline coloring side, we have the freedom to permute the colors. That's something that we will use. So we will create these 3 green edges. So you see the 3 green edges. We create them one by one. To create the first one, we release 1 copy of the gadget. The gadget has the nice feature also, that's how it was created, that there are 2 online colors that are assigned vertices of the same offline color. So there are like two JI, such that for one feasible offline coloring, they are the same color. In particular, I can find 1 representative of the 3 online colors each, so that they don't exhaust all the colors. So I can pick like 1 vertex that the algorithm colored J1, another one the algorithm colored J2, and another one the algorithm colored J3. And I can pick them in such a way that there is an offline coloring that doesn't color all of them the same color. So in this case, it's like yellow and blue. And if I pick those 3 and I connect them to a vertex, then the algorithm has a problem, and it will have to create like 2 vertices of the same online color, just like we had before. But I won't have a problem, because I will be able to color the new vertex red, which is why in this case, I want to call the gadget a red palette. Why? Because if I add a vertex and if I connect it to this system of representatives that I can always find, I am still allowed to color my new vertex red. So the gadget helps me color the vertex red. And now we don't know, of course, which online color the algorithm assigns this red vertex. It could be J1, J2, J3. We have no control over what the algorithm is doing, because we are showing that any algorithm is bad, so we have to brace ourselves for an arbitrary algorithm. But we know that it assigns some color, and in that color, there are now two vertices of the same online color. So that already achieves our first green edge. If you can recall, so those two were like, so the green edges had the property that they had two vertices of the same color. And now we have one of those. But the problem is we don't know in which one. So we can't just repeat this process 3 times and call it a day, because the algorithm could always pick the same, let's say, all the time. Every time we do it, it colors the last vertex in the color J1, then we don't make any progress. Which is why the algorithm, our argumentation gets a bit more complicated in the near future. To obtain a second green edge, our strategy is to force 2 edges, and then we can say at least one of them is in a different color than the first one. And to do that, we introduce 3 palettes. So the one that we have seen, which was a red palette, we do it like 3 times and color them in different ways. And we also connect the 3 last vertices that we add to each other in a hyperedge of size 3. Now the algorithm cannot put W1, W2, and W3 all in the same vertex. And it could use 3 different colors. It could also use 2 different colors. If it used 2 different colors, then that's an edge. And if it uses 3 different colors, then as you see, like these all induce like some of the edges. And in any case, this construction gives us at least 2 edges in the same connected component that are green for the previous definition of green. And one of them is our second green edge. Unfortunately, we still have to have the first one and not say, okay, so this construction gives us 2 green edges, let's have them, because the green edges are forced now to be in different connected components so that we can permute the offline coloring. All right. So now we have got the second green edge. And here the practical case was that W1, W2, and W3 cannot all end up in the same online color, because then we wouldn't have gotten two different edges. And now we want to find something that uses all 3 colors. So here we can't avoid if W1 and W2 are both, let's say, in J1, then we get like 2 edges, 2 green edges, or like actually we get 3 of them, but 2 of them are the same online color, so we can use only 1 out of the 2, and then we get the third one. But in the next step, we will want 3 parallel green edges, so that at most 2 of them can already be of the used online colors. And to that end, that's the most tricky part of the construction. Namely, we will have to think of some subgraph that eventually is forced to admit all 3 online colors. And if you recall the very beginning of the discussion, that is our gadget, which we use all the time to create these palettes. In fact, so here, again, the algorithm could still assign W1 and W2 to J1, and then this doesn't happen. But if you replace the triangle that you see by the entire gadget, then it can happen at most 6 times that the algorithm doesn't use all 3 colors on the gadget. So instead, we get something like this. So here you see like the vertices that are given in the palettes. These are just like exemplary, that they could also look completely different. But the point is, in a red palette, it's possible to not color any of them red. In a blue palette, it's possible to not color any of them blue. And then you can just release a gadget without knowing what the algorithm is doing with it, fix some feasible offline coloring that you see in the picture. And then always, if you colored some vertex yellow, you release it so that it is connected to the yellow palette. And if it's red, then it's connected to the red palette, and so on. This way, you could ask yourself, how many colors does the algorithm use to now color these middle vertices? And the answer is eventually bound to be 3. It can fail to be 3 at most 6 times. Because if that happens more than 6 times, we forget all the palettes, everything we have done, and we go back to the first case where we had played this endgame. So eventually, we get the 3 parallel green edges and take one of them. And then we have exactly a situation that looks like this and can add one last vertex to force a monochromatic edge on one of the online colors. And so if you just count all of the hyperedges and vertices you need for this, it turns out there are 233 hyperedges and, if I'm not mistaken, something like 98 vertices or something like that. And that is, of course, only in the special case that kx equal 3. And what if, sorry, if m is equal 3, like the number of colors is equal 3. So what if we have more than that? Then this will fail because the algorithm will have more choices to assign the hyperedges. And for that, we need a completely different setting that kind of allows to be extended in an arbitrary number of colors. That is unfortunately even much more complicated than here, so I'm not able to show it today. But that particular construction has implications about also the classical online hypergraph coloring problem. So let's recall what it was. Again, we have vertices revealed one index at a time. The first difference is that the hyperedges are revealed upon the revelation of the last vertex. So in our setting, we always know of the partial hyperedges if we, as much as we know its vertices. But in the classical problem, if you have a hyperedge of size 8, you don't know anything about that hyperedge until the 8th vertex is released. And now the task is to find a coloring that completely avoids monochromatic hyperedges. As you see, this is a different task than ours. We wanted to minimize the maximum occurring number, but our construction already exploited the non-possibility of a monochromatic hyperedge. So we have hope that what we have done, at least in the general setting that I'm not showing you, could have implications for the classical problem as well. For an example, this coloring is not feasible because you have a monochromatic edge 1, 2, 3, whereas this coloring that you see here is feasible because it doesn't have a monochromatic edge. Note that it doesn't have Makespan 1, so this wouldn't have been the best possible coloring with respect to our task, but in the classical setting, this is good enough because there is no monochromatic edge. All right. So what does our work imply? Let's see. So for hypergraph coloring, it's really bad. Like you can't get any competitive ratio that is better than omega of n. And that also is true even if you know the partial hyperedges, which is like an unpublished result. It's not part of this paper. Maybe it's part of the next one. So it made sense to look at hypertrees, which you can imagine as like hypergraphs that don't have hypercycles, which is like if you kind of go around, you can go around like vertices such that you always change the hyperedge and eventually you end up where you started. And so the interesting case is something like hypertree, because for hypertrees, there is a better bound known for the classical problem, which is log n, and it's known for the last 2 years that it's also asymptotically best possible. And what I haven't told you is that this generalized construction that I'm not showing you, that also only uses hypertrees. So if I apply that to the general setting, then what happens is that I could be improving the general setting in the special case of hypertrees. Well, the thing is, this whole knowing partial hyperedges, whether knowing the partial hyperedges improves any competitive ratio, whether it offers any improvement, that's not known. That wasn't studied at all. And what our construction delivers is a very, very, very small, however non-constant asymptotic lower bound. So for this case, hypertrees, the classical problem is completely settled, at least up to constants. And we still have a very large gap, namely, our theorem kind of implies that you cannot get a ratio better than S log 5 of n. This S log 5 is the inverse function to n to the n to the n to the n to the n. So you can imagine it's rather slow. However, it's non-constant. So there is no constant ratio competitive algorithm for hypertrees, even if you know the partial edges in advance. This might sound like it's not a big result, to be honest. However, it's also not clear because hypertrees have a lot of structure. That's an extreme restriction. So if you know the partial hyperedges, then there is actually not much you can do, because you're only connecting vertices to other vertices that were already connected to each other. So in some sense, to me at least, it wasn't entirely clear that there should be a non-constant bound. As it turns out, there is. So here is again an overview of the results that we had eventually started with, which was the machine scheduling realm. There we established that if you have two machines, we have the complete picture. For two scenarios, it's 1.6 something. From 3 scenarios onwards, every algorithm is the worst algorithm. And for others, we have also some bounds, but the main upshot is if you increase the number of these scenarios enough, eventually every algorithm will be the worst algorithm. And what we did is also with some implications for the classical online hypergraph coloring problem. In some special case, that's not been studied yet, but I think it's quite curious. And if anyone wants to work on it, then I would be more than happy to communicate about my findings so far. So that brings me to the end of this talk. Thank you very much for your attention. You see the QR code that takes you to the archive page of my paper. Once again, if you have any questions, I would be very happy to answer them. Thank you.
All right, let's thank the speaker. Does anyone have any questions for Ekin?
I have a question. So, how should I be thinking of these scenarios in terms of like if I wanted to implement this, like I had some machines, like should I be thinking of them as like if because they feel almost like pre-processing in some sense. It's like, okay, well if I have these guys together, then I have something, you know, I don't know. It's kind of a soft question, but like, does that make sense at all?
Yeah,
Like how should I think of them?
so my almost whole research is about these scenario models. And in general, if it's not an online problem, we always want to model them as like, that's why they're called scenarios, different outcomes, and you want to brace yourself for the worst outcome. If you're looking at an online problem, that's kind of a silly way to think about it, because like the uncertainty aspect is already the temporal aspect that you're incrementally gaining
Right.
information. In this problem, I kind of see the scenarios as like certain aspects of the same thing. So maybe like you have some, I don't know, some services, right? And each customer has some subset of the services that they would want. and then you kind of want to you want to balance it for every single service. Maybe these are like different rooms. Another interpretation I came up with was like when you're grading an exam and not every student has answered every question, but you have designated people grading some questions. So you want to balance it for every grading team without kind of ripping the exams apart.
I see. Cool. Thank you.
Any other questions? Okay, so let's think again. We can stop the recording. Maybe